different vantage point. This problem was supposed to point out something that we couldn't talk about before until we really saw it. And I'm not sure that some of you even saw it yesterday, but the idea here is that this system, hold on just a minute, border white, fill that and that. This is the picture, right? With point P right here. And the question asks, determine the magnitude and direction of the induced electric field at point P and indicate its direction on the diagram above. Well, at this point, we know the direction of that electric field from our conversation yesterday, but it was right at the very end, so I kind of want to reiterate it. The thing that pushes the charges around has to be an electric field. It has to be. And as I tried to say yesterday, and I'm not sure with the kind of success I wanted, the rules of physics are invariant. And I love saying it that way because it wasn't like these rules were just thought out willy-nilly. They were created by watching and looking at the universe closely. Through careful observation and experiment, rules have been developed to help explain the nature of the universe. What's amazing to me is we still are going back to Isaac Newton. 400 years ago, Isaac Newton, looking at his work on the idea of force and inertia, that they still form the basis for even a complex idea like this, that charged particle can't go anywhere unless something pushes on it. That force has to come from somewhere. That is not just something that's magically made up. And that's why I tried to build up to this point over the course of a couple of days. That there are three things that seem to be causing this EMF. And the first two were easy to see. Motional EMF is easy to see. It's easy to talk about. I can grab that right-hand rule. We can talk about the force on charged particles. You can pick up the paper clips and know it's there. That was pretty straightforward. This one, that just the magnetic field changing makes a current, that was tough. But when we got right back down to the basics, the fundamentals, that charged particle can only move if there's a force acting on it, which means that as this magnetic field changes, and in the course of this problem, we know that it's becoming greater into the page, then there has to be an induced current in the loop. Right-hand rule or nothing, that induced current has to be to oppose this change, which means it has to create a magnetic field in the middle of the loop that's out of the page, which creates a counterclockwise current. Now, all of that is just kind of us willy-nilly applying these rules that we know about. But the actual thing that causes the charges to move has to be an electric field. That way, the charge experiences a force from that electric field. It's the only way. A charge cannot be started into motion without there being an electric field acting on it. And what that ultimately means is that there's an electric field that's in a circle all the way around this loop, that there's a circular electric field. It's weirder than that. There are concentric circular electric fields. That emanate from the inside of your magnetic field. Now, I find this to be bizarre, and I'm gonna be obvious with you guys that there's parts of this that don't make sense to me. Studying this for 30 years, there's parts of it that just don't seem to fall into place for me. Like, why is there an epicenter to these circular electric fields? Why doesn't it form like vortexes and lots of little electric field things? Why is it like this? There is an answer to that question, but and it has to do with flux and the size of the changing magnetic field. These things all play a role in determining why it's epicenter just like this. It exists like this because the electric field behaves according to where the flux is that you're looking at. Meaning if I put a loop of wire there, that centers the flux. The change in magnetic field is through the loop that I centered there. And therefore the electric field that acts centered based on that loop. What's interesting is this electric field is here whether there's a loop of conductor or not. That's why the problem goes on to just put an electron in a glass tube. To talk to you about the force on a single point particle, an electron stuck in a tube. This electric field is real. It's not just because there's a conductor there. Any changing magnetic field produces an electric field. It is a circular electric field, which means there's now two ways to produce an electric field. The first way is to just place a positive particle and a negative particle someplace. I put an electron and a proton somewhere, and I have an electric field. But the second way to produce an electric field is to change a magnetic field. Now, I'd love to say that this is the end of the story, that this is where Faraday's law ends. It doesn't. But I do need to do a few things here so that I feel like you guys are well educated about this. The first thing I want to remind you is that means that we could discuss the amount of electric potential for the loop. Can't call it a potential difference anymore, because if we integrate this across the loop, we end up back where we started. So this isn't a potential difference, but it doesn't change the fact that it creates an EMF, that the amount of energy in this loop can be taken by looking at the integral around the loop. So, instead of looking at the EMF from the standpoint of a change in flux, we could write the EMF from the standpoint of doing the work about the electric field, but we need to make sure we encompass the entire loop. And these must be equal, which produces now this is how you calculate the electric field from a changing magnetic field. Now, to do so is not easy. Some of you are going to have trouble with this. And I want to try and make this as clear as possible. The right side of this hasn't changed. The right side of this is still about finding flux. So I have some students who are having this loop of charge. We know from the problem itself that this loop of charge has radius r, right? And we have a changing magnetic field. If I everywhere in the loop, it has to be. You understand what I'm saying, right? That the electric field, this electric field, the yellow arrows, all have to be the same size, because the current that's produced is a constant current. So the electric field that must be causing that current has to be a constant electric field. So in this integral that I have, difficulty with that. So let's talk about finding flux for just a minute more. And I know that this is redundant for some of you, and I get it, but just feel a little bit of, sympathy for some folks who every time this comes up, look me in the eyes and say, I have no idea where to begin, as they stare down at their paper and won't make eye contact. Flux is about looking for three things. It's about looking at how much magnetic field there is, how much area it takes up, and what the angle between the magnetic field and the area is. The grand scope is that you're always going to get three pieces in the end. No matter what, you'll have three pieces in the end of calculating flux. You need to look at the shape of the area in question. You have to decide if the magnetic field is constant or changing everywhere inside that shape. And you do need to take into consideration the angle that the area makes with respect to the magnetic field. Those three questions, if you didn't write them down just now, would you do it finally? So I don't have to repeat myself. What is the shape of the object where the magnetic field is? What is the strength of that magnetic field? And does it vary inside the shape? Does it change as you go from one part of the shape to another part of the shape? And what is the angle between the surface area and the magnetic field? That's how you calculate flux, any flux, albeit electric field or magnetic field. We're talking about magnetic flux. Now, if the area is changing or the angle is changing, there isn't an electric field produced. Let me say that again. If the area is changing or the angle is changing, there is not an electric field produced. If those two things are changing, we're getting a motional EMF. We're getting a direct force on the charged particles due to the magnetic field. It's only when the magnetic field is changing that there's a created electric field. That's the only time. I mean, ultimately, you could write our rule a little different. You could write our rule I'm leaving out the N and I'm leaving out the negative sign for just a minute to state that you could say that our rule is this. Because it only exists, this electric field is only there when there's a changing magnetic field. Okay. So, getting back to this, I want to point out that you will be asked to calculate the electric field from a changing magnetic field, and it happens right here. This is the point where you would do that. And it's not as hard as it looks. If we apply it to the problem we're dealing with right now, where I have used that alone, the electric field will be constant. The electric field, oops, you guys don't like red. The electric field comes out of the integral, and all that says is to add up the length of a loop that is a circle, which you guys all know is 2 pi r. And the area inside my circle and the rate of change of the magnetic field. By the way, when we're done with this, you have the electric field from any magnetic field. This is the size of the electric field from any changing magnetic field. R represents the distance from the center of the field, the center of the magnetic field. What's crazy What's really crazy is our units have to work out here. Right? Apparently multiplying the rate of change of a magnetic field by a distance gives you the size of an electric field. It has to. Right? The units have to work out. Everything else canceled. I don't know if you remember this, but we talked about work done in an electric field a long time ago. And we said that the work done in an electric field would be F dot dx, just like our definition of work in mechanics. You all right with that, Owen? Good, good, good. If we go way back to our our discussion about this, you'll remember that we talked about the electric force coming directly from the electric field. So we could say the work done in our electric field now, continuing on from here, I want to remind you that this is a dot product. We're calculating work. And this would be the work done in moving a charged particle through an electric field. Work done by the field, if you like. Now, the next step here is to recognize that the charge can be put out front, right? Moving a charge isn't changing as it moves through an electric field. So we had this is first semester, so we've already seen this, right? This is our definition of electric potential as defined by the field in moving a charge against or with a field. Now, if you'll remember, there's a lot to the negatives and positive signs here. We talked about moving a charge against the electric field. We were gaining electric potential. If we moved the charge with the electric field, we were losing electric potential. And we had to recognize that the work was opposite the potential energy. So the work done by the field on the particle caused it to lose potential energy. Right? If you drop a pencil in a gravitational field, the work done by gravity bringing it to the ground causes the object to lose potential energy. But if you do work against the field, the object gains potential energy. I'm just reminding you about how the negative sign works here, because Tyler's awful worried about the negative signs. Now, stating this and applying it here